Hello, Namaste. Myself Ankita Shreya Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ART.SKILL.PASSION. Chapter 11, Dual Nature of Radiation and Matter. 11.1 Introduction. The Maxwell's equation of electromagnetism and Hertz experiment on the generation and detection of electromagnetic waves in 1887 strongly established the wave nature of light. Towards the same period at the end of the 19th century, experimental investigations on conduction of electricity, electric discharge through gases at low pressure in a discharge tube led to many historic discoveries. The discovery of X-rays by Roentgen in 1895 and electron by J.J. Thomson in 1897 were important milestones in the understanding of atomic structure. It was found that at sufficiently low pressure of about 0.001 mm of mercury column, a discharge took place between the two electrodes on applying the electric field to the gas. In the discharge tube, a fluorescent glow appeared on the glass opposite to the cathode. The color of glow of the glass depends on the type of glasses, is being yellowish green for soda glass. The cause of this fluorescence was attributed to the radiation which appeared to be coming from the cathode. These cathode rays were discovered in 1870 by William Crookes, who later in 1879 suggested that these rays consisted of streams of fast-moving negatively charged particles. The British physicist J.J. Thomson 1856 to 1940 confirmed this hypothesis. By applying mutually perpendicular electric and magnetic fields across the discharge tube, J.J. Thomson was the first to determine experimentally the speed and the specific charge to mass ratio E/m of the cathode ray particles. They were found to travel with speeds ranging from about 0.1 to 0.2 times the speed of light. 3 into 10 to the power 8 meter per second. The presently accepted values of E/m is 1.76 into 10 to the power 11 C by kg. Further, the value of E/m was found to be independent of the nature of the material metal used as cathode, emitter, or the gas introduced in the discharge tube. This observation suggested the universality of the cathode ray particles. Around the same time in 1887, it was found that certain metals, when irradiated by ultraviolet light, emitted negatively charged particles having small speeds. Also, certain metals, when heated to a high temperature, were found to emit negatively charged particles. The value of E/m of these particles was found to be the same as that for cathode ray particles. These observations thus established that all these particles, although produced under different conditions, were identical in nature. J.J. Thomson in 1897 named these particles as electrons and suggested that they were fundamental universal constituents of matter. For his epoch-making discovery of electron, through his theoretical and experimental investigation on conduction of electricity by gases, he was awarded the Nobel Prize in Physics in 1906. In 1913, the American physicist R.A. Millikan 1868 to 1953 performed the pioneering oil drop experiment for the precise measurement of the charge on an electron. He found that the charge on an oil drop was always an integral multiple of an elementary charge 1.602 into 10 to the power minus 19 coulomb. Millikan experiment established the electric charge is quantized. From the value of charge E and specific charge E by m, the mass m of the electron could be determined. 11.2 Electron emission. We know that metal have free electrons, negatively charged particles that are responsible for their conductivity. However, the free electrons cannot normally escape out of the metal surface. If an electron attempts to come out of the metal surface acquires a positive charge and pulls the electron back to the metal. The free electron is thus held inside the metal surface by the attractive forces of the ions. Consequently, the electron can come out of the metal surface only if it has got sufficient energy to overcome the attractive pull. A certain minimum amount of energy is required to be given to an electron to pull it out from the surface of the metal. This minimum energy required by an electron to escape from the metal surface is called the work function of the metal. It is generally denoted by integral naught and measured in eV, electron volt. 1 electron volt is the energy gained by an electron when it has been accelerated by a potential difference of 1 volt, so that 1 eV is equal to 1.602 into 10 to the power minus 19 joule. This unit of energy is commonly used in atomic and nuclear physics. The work function loop integral naught depends on the properties of the metal and the nature of its surface. The values of work function of some metals are given in table 11.1. These values are approximate as they are very sensitive to surface impurities. Note from table 11.1 that the work function of platinum is the highest. Loop integral naught is equal to 5.65 eV, while it shows the lowest loop integral naught is equal to 2.14 eV for cesium. The minimum energy required for the electron emission from the metal surface can be supplied to the free electrons by any one of the following physical processes. Thermionic emission. By suitable heating, sufficient thermal energy can be imparted to the free electrons to enable them to come out of the metal. Second, field emission. By applying a very strong electric field of the order of 10 to the power 8 volt meter to the power of minus 1 to a metal, electrons can be pulled out of the metal as in a spark plug. Third, photoelectric emission. When light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. These photolight generated electrons are called photoelectrons. 11.3 Photoelectric Effect. 11.3.1 Hertz observation. The phenomenon of photoelectric emission was discovered in 1887 by Heinrich Hertz, 1857 to 1894, during his electromagnetic wave experiment. In his experimental investigation on the production of electromagnetic waves by means of a spark discharge, Hertz observed that high voltage spark across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Light shining on the metal surface somehow facilitated the escape of the free charge particles, which we know now known as electrons. When the light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space. 11.3.2 Hallwach's and Lenard's observation. Wilhelm Hallwach's and Philip Lenard investigated the phenomena of photoelectric emission in detail during 1886-1902. Lenard 1862 to 1947 observed that when ultraviolet radiations were allowed to fall on the emitter plate of an evacuated glass tube enclosing two electrodes, metal plates, current flows in the circuit. Figure 11.1. As soon as the ultraviolet radiation was stopped, the current flow also stopped. These observations indicate that when ultraviolet radiation falls on the emitter plate C, electrons are ejected from it, which are attracted towards the positive collector plate A by the electric field. The electrons flow through the evacuated glass tube, resulting in the current flow. The light falling on the surface of the emitter causes current in the external circuit. Hallwatches and Lenard studied how this photocurrent varied with collector plate potential and with frequency and intensity of incident light. Hallwatches in 1888 undertook the study of further and connected a negatively charged zinc plate to an electroscope. He observed that the zinc plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged when it was irradiated by ultraviolet light. Positive charge on a positively charged zinc plate was found to be further enhanced when it was illuminated by ultraviolet light. From these observations, he concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. After the discovery of the electron in 1897, it became evident that the incident light causes electrons to be emitted from the emitter plate. Due to negative charge, the emitted electrons are pushed towards the coil collector plate by the electric field. Hallwatches and Lenard also observed that when ultraviolet light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value called the threshold frequency. This minimum frequency depends on the nature of the material of the emitter plate. It was found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light, having short wavelength to cause electron emission from the surface. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive even to visible light. All these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons. The phenomenon is called photoelectric effect. 11.4 Experimental study of photoelectric effect. Figure 11.1 depicts a systematic view of the arrangement used for the experimental study of the photoelectric effect. It consists of an evacuated glass quartz tube having a thin photosensitive plate C and another metal plate A. Monochromatic light from the source S of the sufficiently short wavelength passes through the window W and falls on the photosensitive plate C, emitter. A transparent quartz window is sealed onto the glass tube, which permits ultraviolet radiation to pass through it and irradiate the photosensitive plate C. The electrons are emitted by the plate C and are collected by the plate A collector. By the electric field created by the battery maintains the potential difference between the plates C and A that can be varied. The polarity of plates C and A can be reversed by a commutator. Thus, the plate A can be maintained at a desired positive or negative potential with respect to emitter C. When the collector plate A is positive with respect to the emitter plate C, the electrons are attracted to it. The emission of electrons causes flow of electric current in the circuit. The potential difference between the emitter and collector plates is measured by a voltmeter V, whereas the resulting photocurrent flowing in the circuit is measured by a microammeter URA. The photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. The intensity and frequency of the incident light can be varied, as can the potential difference V between the emitter C and the collector A. We can use the experimental arrangement of figure 11.1 to study the variation of photocurrent with A. Intensity of radiation, B. Frequency of the incident radiation, C. The potential difference between the plates A and C, and D. The nature of material of plate C. Light of different frequency can be used by putting appropriate color filter or colored glass in the path of light falling on the emitter C. The intensity of light is varied by changing the distance of the light source from the emitter. 11.4.1 Effect of intensity of light on photocurrent. The collector A is maintained at the positive potential with respect to emitter C, so that electrons ejected from C are attracted towards collector A, keeping the frequency of the incident radiation and the potential fixed. The intensity of light is varied and the resulting photoelectric current is measured each time. It is found that the photocurrent increases linearly with intensity of incident light, as shown graphically in figure 11.2. The photocurrent is directly proportional to the number of photoelectrons emitted per second. This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. 11.4.2 Effect of potential on photoelectric current. We first keep the plate A at some positive potential with respect to the plate C and illuminate the plate C with light of fixed frequency V and fixed intensity I1. We next vary the positive potential of plate A gradually and measure the resulting photocurrent each time. It is found that the photoelectric current increases with the increase in positive accelerating potential. At some stage, for a certain positive potential of plate A, all the emitted electrons are collected by the plate A and the photoelectric current becomes maximum or saturates. If we increase the accelerating potential of plate A further, the photocurrent does not increase. This maximum value of the photoelectric current is called saturation current. Saturation current corresponds to the case when all the photoelectrons emitted by the emitter plate C reach the collector plate A. We now apply a negative retarding potential to the plate A with respect to the plate C and make it increasingly negative gradually when the polarity is reversed. The electrons are repelled and only the sufficiently energetic electrons are able to reach the collector A. The photocurrent is found to decrease rapidly until it drops to zero, a certain sharply defined critical value of the negative potential V0 on the plate A. For a particular frequency of incident radiation, the minimum negative retarding potential V0 given to the plate A for which the photocurrent stops or becomes zero is called the cutoff or stopping potential. The interpretation of the observation in terms of photoelectrons is straightforward. All the photoelectrons emitted from the metal do not have the same energy. Photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy Kmax, so that Kmax is equal to eV0. We can now repeat this experiment with incident radiation of the same frequency but of higher intensity, I2 and I3. I3 greater than I2 greater than I1. We note that the saturation current are now found to be at higher values. This shows that more electrons are being emitted per second, proportional to the intensity of incident radiation. But the stopping potential remains the same as that for the incident radiation of intensity I1, as shown graphically in figure 11.3. Thus, for a given frequency of the incident radiation, the stopping potential is independent of its intensity. In other words, the maximum kinetic energy of photoelectrons depends on the light source and the emitter plate material, but is independent of intensity of incident radiation. 11.4.3 Effect of frequency of incident radiation on stopping potential. We now study the relation between the frequency V of the incident radiation and the stopping potential V0. We suitably adjust the same intensity of light radiation at various frequencies and study the variation of photocurrent with collector plate potential. The resulting variation is shown in figure 11.4. We obtain different values of stopping potential but the same value of the saturation current for incident radiation of different frequencies. The energy of the emitted electrons depends on the frequency of the incident radiations. The stopping potential is more negative for higher frequency of incident radiation. Note from figure 11.4 that the stopping potential are in the order V03 greater than V02 greater than V01 if the frequencies are in order V3, V2, V1 in decreasing order. This implies that greater the frequency of incident light, greater is the maximum kinetic energy of the photoelectrons. Consequently, we need greater retarding potential to stop them completely. If we plot a graph between the frequency of incident radiation and the corresponding stopping potential for different metals, we get a straight line as shown in figure 11.5. The graph shows that the stopping potential V0 varies linearly with the frequency of incident radiation for a given photosensitive material. Second, there exists a certain minimum cut-off frequency V0 for which the stopping potential is 0. These observations have two implications. First, the maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation but is dependent of its intensity. For a frequency V of incident radiation lower than the cut-off frequency V0, no photoelectric emission is possible even if the intensity is large. The minimum cut-off frequency V0 is called the threshold frequency. It is different for different metals. Different photosensitive materials respond differently to light. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives different response to light of different wavelengths. For example, ultraviolet light gives rise to photoelectric effect in copper while green or red light does not. Note that in all the above experiments, it is found that a frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously without any apparent time lag. Even if the incident radiation is very dim, it is now known that emission starts in the time of the order of 10 to the power minus 9 seconds or less. We now summarize the experimental features and observation described in this session. First, for a given photosensitive material and frequency of incident radiation above the threshold frequency, the photoelectric current is directly proportional to the intensity of incident light. Figure 11.2. For a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity. Third, for a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation, called the threshold frequency, below which no emission of photoelectrons takes place. No matter how intense the incident light is above the threshold frequency, the stopping potential, or equivalently the maximum kinetic energy of the emitter photoelectrons, increase linearly with the frequency of the incident radiation, but is independent of its intensity. Figure 11.5. Fourth, the photoelectric emission is an instantaneous process without any apparent time lag. 10 to the power minus 9 seconds or less, even when the incident radiation is made exceedingly dim. 11.5. Photoelectric effect and wave theory of light. The wave nature of light was well established by the end of the 19th century. The phenomenon of interference, diffraction, and polarization were expanding in a natural and satisfactory way by the wave picture of light. According to this picture, light is an electromagnetic wave consisting of electric and magnetic fields with continuous distribution of energy over the region or space over which the wave is extended. Let us now see if this wave picture of light can explain the observation on photoelectric emission given in the previous session. According to the wave picture of light, the free electrons at the surface of the metal over which the beam of radiation falls absorb the radiant energy continuously. The greater the intensity of radiation, the greater are the amplitude of electric and magnetic fields. Consequently, the greater the intensity, the greater should be the energy absorbed by each electron. In this picture, the maximum kinetic energy of the photoelectrons on the surface is then expected to increase with increase in intensity. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation over sufficient time should be able to impart enough energy to the electrons so that they exceeded the minimum energy needed to escape from the metal surface. A threshold frequency therefore should not exceed these expectations of the wave theory. Directed contradict observation. First, second and third given at the end of subsection 11.4.3. Further, we should note that in the wave picture, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. Since a large number of electrons absorb energy, the energy absorbed per electron per unit time turns out to be small. Explicit calculation estimate that it can take hours or more for a single electron to pick up sufficient energy to overcome the work function and come out of the metal. This conclusion is again in striking contrast to observation 4, that the photoelectric emission is instantaneous in short. The wave picture is unable to explain the most basic feature of photoelectric emission. 11.6 Einstein's photoelectric equation, energy quantum of radiation. In 1905, Albert Einstein 1879 to 1955 proposed a radically new picture of electromagnetic radiation to explain photoelectric effect. In this picture, photoelectric emission does not take place by continuous absorption of energy from radiation. Radiation energy is built up of discrete units, the so-called quanta of energy of radiation. Each quantum of radiant energy has energy hv, where h is Planck's constant and v the frequency of light. In photoelectric effect, and an electron absorbs a quantum of energy hv of radiation. If this quantum of energy absorbed exceeds the minimum energy needed for the electron to escape from the metal surface, work function loop integral, the electron is emitted with maximum kinetic energy. Kmax is equal to hv minus loop integral naught. More tightly bound electrons emerge with kinetic energy less than the maximum value. Note that the intensity of light of a given frequency is determined by the number of protons incident per second. Increasingly, the intensity will increase the number of emitted electrons per second. However, the maximum kinetic energy of the emitted photoelectrons is determined by the energy of each photon. Equation 11.2 is known as Einstein photoelectric equation. We now see how this equation accounts in a simple and elegant manner all the observation on photoelectric effect given at the end of subsection 11.4.3. According to equation 11.2, Kmax depends linearly on V and is independent of intensity of radiation in agreement with observation. This has happened because an Einstein picture photoelectric effect arises from the absorption of a single quantum of radiation by a single electron. The intensity of radiation, that is proportional to the number of energy quanta per unit area per unit time, is irrelevant to this basic processes. Since Kmax must be non-negative, equation 11.2 implies that photoelectric emission is possible only if hv greater than loop integral or v greater than v naught, where v naught is equal to loop integral naught by h. Equation 11.3 shows that the greater the work function loop integral naught, the higher the minimum or threshold frequency v naught need to emit photoelectrons. Thus, there exists a threshold frequency v naught is equal to loop integral naught by h for the metal surface below which no photoelectric emission is possible, no matter how intense the incident radiation may be or how long it falls on the surface. In this picture, intensity of radiation as noted above is proportional to the number of energy quanta per unit area per unit time. The greater the number of energy quanta available, the greater is the number of electrons absorbing the energy quanta, and greater therefore is the number of electrons coming out of the metal for V greater than V naught. This explains why for V greater than V naught photoelectric current is proportional to intensity. In Einstein's picture, the basic elementary processes involved in photoelectric effect is the absorption of light quantum by an electron. This process is instantaneous. Thus, whatever may be the intensity, that is the number of quanta or radiation per unit area per unit time, photoelectric emission is instantaneous. Low intensity does not mean delay in emission. Since the basic elementary processes is the same intensity, only determines how many electrons are able to participate in the elementary processes. Absorption of a light quantum by a single electron, and therefore the photoelectric current using equation 11.1. The photoelectric equation 11.2 can be written as EV0 is equal to HV minus loop integral naught for V greater than V0, or V0 is equal to H by E V minus loop integral naught by E. This is an important result. It predicts that the V0 versus V curve is a straight line with slope is equal to H by E. Independent of the nature of the material, during 1906 to 1916, Millikan performed a series of experiments on photoelectric effect aimed at disproving Einstein's photoelectric equation. He measured the slope of the straight line obtained for sodium similar to the shown in figure 11.5. Using the known value of E, he determined the value of Planck's constant H. This value was close to the value of Planck's constant, is equal to 6.626 into 10 to the power minus 34 joule per seconds, determined in an entirely different context. In this way, in 1916, Millikan proved the validity of Einstein's photoelectric equation instead of disapproving it. The successful explanation of photoelectric effect using the hypothesis of light quanta and the experimental determination of values of H and loop integral naught in the agreement with the values obtained from other experiments led to the acceptance of Einstein's picture of photoelectric effect. Millikan verified photoelectric equation with great precision for a number of alkali metals over a wide range of radiation frequencies. 11.7 Particle nature of light. The photon. Photoelectric effect thus give evidence to the strange fact that light in interaction with matter behaved as if it was made of quanta or packets of energy. Each of energy HV is the light quantum of energy to be associated with a particle. Einstein arrived at the important result that the light quantum can also be associated with momentum HV by c. A definite value of energy as well as momentum is a strong sign that the light quantum can be associated with particle. This particle was later named photon. The particle-like behavior of light was further confirmed in 1924 by the experiment of A.H. Compton, 1892 to 1962, on scattering of X-rays from electrons. In 1921, Einstein was awarded the Nobel Prize in Physics for his contribution to theoretical physics and the photoelectric effect. In 1923, Millikan was awarded the Nobel Prize in Physics for his work on the elementary charge of electricity and on the photoelectric effect. We can summarize the photon picture of electromagnetic radiation as follows. First, in the interaction of radiation with matter, radiation behaves as if it is made up of particles like photons. Second, each photon has energy E is equal to hv and momentum P is equal to hv by c, and speed c, the speed of light. Third, all photons of light of a particular frequency v or wavelength lambda have the same energy. E is equal to hv is equal to hc by lambda, and momentum P is equal to hv by c is equal to h by lambda. Whatever the intensity of radiation may be, by increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area. With each photon having the same energy, the photon energy is independent of intensity of radiation. Fourth, photons are electrically neutral and are not deflected by electric and magnetic fields. Fifth, in photon particle collision such as proton-electron collision, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision. The photon may be absorbed or a new photon may be created. 11.8 Wave nature of matter. The dual wave particle nature of light, electromagnetic radiation in general, comes out clearly from what we have learned in this and the preceding chapters. The wave nature of light shows up in the phenomena of interference, diffraction, and polarization. On the other hand, in photoelectric effect and Compton effect, which involves energy and momentum transfer, radiation behaves as if it is made up of a bunch of particles, the photons. Whether a particle or wave description is best suited for understanding an experiment depends on the nature of the experiment. For example, in the similar phenomenon of seeing an object by our eye, both descriptions are important. The gathering and focusing mechanism of light by the eye lens is well described in the wave picture, but its absorption by the rods and cones of the retina requires the photon picture of light. A natural question arises: if the radiation has dual wave particle nature, might not the particles of nature, the electron, protons, etc. also exhibit wave-like character? In 1924, the French physicist Louis Victor de Broglie, pronounced as de Broglie, 1892 to 1987, put forward to the Bloch hypothesis that moving particles of matter should display wave-like properties under suitable conditions. He reasoned that the nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. If radiation shows dual aspects, so should matter. De Broglie proposed that the wavelength lambda associated with a particle of momentum p is given as lambda is equal to h by p is equal to h by mv, where m is the masses of the particle and v its speed. Equation 11.5 is known as the de Broglie's relation, and the wavelength lambda of the matter wave is called de Broglie's wavelength. The dual aspects of matter is evident in the de Broglie's relation. On the left hand side of equation 11.5, lambda is the attribute of a wave, while on the right hand side the momentum p is a typical attribute of a particle. Planck's constant h relates the two attributaries. Equation 11.5 for a material particle is basically a hypothesis whose validity can be tested only by experiment. However, it is interesting to see that it is satisfied only by a photon. For a photon, as we have seen, p is equal to hv by c. Therefore, h by p is equal to c by v is equal to lambda. That is the de Broglie's wavelength of a photon given by equation 11.5 equals the wavelength of electromagnetic radiation, of which the photon is a quantum of energy and momentum. Clearly from equation 11.5, lambda is smaller for a heavier particle, large m, or more energetic particle, large v. For example, the de Broglie's wavelength of a ball of mass 0.12 kg moving with a speed of 20 meters per second inverse is easily calculated. P is equal to mv is equal to 0.12 kg into 20 meter per second inverse is equal to 2.40 kg meter per second inverse. Lambda is equal to h by p 6.63 into 10 to the power minus 34 joule per second divided by 2.40 kg meter per second inverse is equal to 2.76 into 10 to the power minus 34 meter. This wavelength is so small that it is beyond any measurement. This is the reason why macroscopic objects in our daily life do not show wave-like properties. On the other hand, in the subatomic domain, the wave character of particles is significant and measurable. Consider an electron mass m, charge E accelerated from rush through a potential V. The kinetic energy K of the electron equals the work done EV on it by the electric field. K is equal to EV. Now K is equal to half mv square is equal to p square by 2m. So that P is equal to root 2 mk is equal to root 2 m EV. The de Broglie's wavelength of the electron is the lambda is equal to h by p is equal to h by root 2 mk is equal to h by root 2 mev. Substituting the numericals value of h m e, we get lambda is equal to 1.227 by root v nm, where v is the magnitude of accelerating potential in volts. For a 120 volt accelerating potential, equation 11.11 gives lambda is equal to 0.112 nanometer. This wavelength is of the same order as the spacing between the atomic planes in crystals. This suggests that matter waves associated with an electron could be verified by crystal diffraction experiments analogous to X-ray diffraction. We describe the experimental verification of the de Broglie's hypothesis in the next session. In 1929, de Broglie was awarded the Nobel Prize in Physics of his discovery of the wave nature of electrons. The matter wave picture elegantly incorporated the Heisenberg's uncertainty principle. According to the principle, it is not possible to measure both the position and momentum of an electron or any other particle at the same time exactly. There is always some uncertainty delta x in superposition of position and some uncertainty delta p is the specification of momentum. The product of delta x and delta p is of the order of h with h is equal to h by 2 pi, that is delta x delta p equivalence to h. Equation 11.12 allows the possibility that delta x is 0, but then delta p must be infinite in order that the product is non-zero. Similarly, if delta p is 0, delta x must be infinite. Ordinarily, both delta x and delta p are non-zero such that their products is of the order of h. Now, if an electron has an definite momentum p, that is delta p is equal to 0. By the de Broglie's relation, it has a definite wavelength lambda. A wave of definite single wavelength extends all over space by Bond's probability interpretation. This means that the electron is not localized in any finite region of space. That is, its position uncertainty is infinite. Delta x is equivalent to infinity, which is consistent with the uncertainty principle. In general, the matter wave associated with the electron is not extended all over space. It is a wave packet extending over some finite region of space. In that case, delta x is not finite but has some finite value depending on the extension of wave packet. Also, you must appreciate that a wave packet of finite extension does not have a single wavelength. It is built up of a wavelength spread around some central wavelength. By de Broglie's relation, then the momentum of electron will also have a spread and uncertainty delta P. This is as expected from the uncertainty principle. It can be shown that the wave packet description together with de Broglie's relation and Bond's probability interpretation reproduce the Heisenberg uncertainty principle exactly. In Chapter 12, the de Broglie's relation will be seen to justify Bohr's postulate on quantization of angular momentum of electron in an atom. Figure 11.6 shows a schematic diagram of a localized wave pocket and B an extended wave with fixed wavelength. 11.9 Davison and Germer experiment. The wave nature of electrons was first experimentally verified by C.G. Davison and L.H. Germer in 1927 and independently by G.P. Thomson in 1928, who observed diffraction effects with beams of electrons scattered by crystal. Davison and Thomson shared the Nobel Prize in 1937 for their experimental discovery of diffraction of electrons by crystals. The experimental arrangement used by Davison and Germer is schematically shown in figure 11.7. It consists of an electron gun which comprises of a tungsten filament F coated with barium oxide and heated by a low voltage power supply LT or battery. Electrons emitted by the filament are accelerated to a desired velocity by applying suitable potential voltage from a high voltage power supply ST or battery. They are made to pass through a cylinder with fine holes along its axis, producing a fine columnated beam. The beam is made to fall on the surface of nickel crystal. The electrons are scattered in all directions by the atoms of the crystal. The intensity of electron beam scattered in a given direction is measured by the electrode detector collector. The detector can be moved on a circular scale and is connected to a sensitive galvanometer, which records the current. The deflection of the galvanometer is proportional to the intensity of the electron beam entering the collector. The apparatus is enclosed in an evacuated chamber. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering theta, which is the angle between the incident and the scattered electron beams. The variation of the intensity I of the scattered electrons with the angle of scattering theta is obtained for different accelerating voltages. The experiment was performed by varying the accelerating voltage from 44V to 68V. It was noticed that a strong peak appeared in the intensity I of the scattered electron for an accelerating voltage of 54 volt at a scattering angle theta is equal to 50 degrees. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regular spaced among of the crystals. From the electron diffraction measurements, the wavelength of matter was found to be 0.165 nanometer. The de Broglie's wavelength lambda associated with the electrons using equation 11.11 for V is equal to 54 volt is given by lambda is equal to H by P is equal to 1227 by root V nanometer. Lambda is equal to 1.227 by root over 54 nanometer is equal to 0.16 nanometer. Thus, there is an excellent agreement between the theoretical value and the experimentally obtained value of de Broglie's wavelength. Davison-Germer experiment thus striking confirms the wave nature of electrons and the de Broglie's relation. More recently, in 1989, the wave nature of a beam of electrons was experimentally demonstrated in a double-slit experiment, similar to that used for the wave nature of light. Also, in an experiment in 1994, interference fringes were obtained with the beam of iodine molecules, which are about 1,000,000 times more massive than electrons. The de Broglie's hypothesis has been basic to the development of modern quantum mechanics. It has also led to the field of electron optics. The wave properties of electrons have been utilized in the design of electron microscope, which is a great improvement with higher resolution over the optical microscope. Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.